Okay. So hello everyone, I'm Shoang, the research fellow in the RI UK in the University of Southampton. Today I'm going to present you my research about the safe and trustworthiness AI. So I will focus on 3 points. One is for the uncertainty quantification, one for failure detection, and for the safety alignment for large language model and vision language model. So first, I want to show you my career journey. So I did my master in National University of Singapore, and then work as the linguistics specialist for 3 years, and then start my PhD from 2021 in the Open University in UK, and then currently is the postdoc in the University of Southampton. So about my research theme, the first one is the trustworthy and responsible AI system. So for example, when we have the inference data, and then we make sure that our system is safe and reliable, and instead of just take the output from our system, we set a rejection threshold. So if the output can pass this rejection threshold, and then we say, okay, this prediction is good enough, but if it cannot, it will be rejected and passed to the human experts. So for example, for the clinician. And another one is for the uncertainty quantification. Here, my work focuses on the confidence calibration. So if you can see in this graph, and this one is the confidence level, and this one is the accuracy. And by default, if the model confidence level and accuracy align with each other, so means that the confidence level is fine. And here you can clearly see that this actually is overconfident, because when let's say the confidence level is only 0.6 and the accuracy is like 0.2. So means that the model is very confidently provide the unsure, even the wrong answer. And another side of the coin is the underconfidence. So means that even though the model already provides the correct answer, but it's not confident enough. And what we want to do is to align these two levels and then make it well-calibrated model. Another one is for the safety alignment for the large language model, because nowadays it's easily to be attacked by the malicious data. So how to make sure that after the fine-tuning, the model still have maintain the safety alignment as the pre-trained one. And then for my work, so nowadays with the, let's say, the transformer-based vision language model and the large language model, we all know that it's well used, and then trained on the massive data set, either on the image or the text or the multimodality model, and with the massive model parameter. So it seems like this large language model, obviously the AI system, has been well applied in many domains. But here comes a very fundamental question. Can we trust them? And then when to trust them? So for my work, the challenge for the model calibration is that while the recent technique focus only on the overconfidence level, but ignore the underconfidence level. And for the automatic failure detection, the existing evaluation metrics don't have sufficient applicability. So for example, that not every domain needs accuracy and not every domain needs, let's say, F1 score as the evaluation. And also for the large language model, as I said before, that it can be easily attacked by the malicious data, and also the excessive high dimensional output make it very difficult to apply the calibration technique. So how to quantify the uncertainty for the large language model in this case? So for my work, the first one for the confidence calibration. So confidence is actually the predicted probability. Means that after you get the logic from the model and then you apply the soft math in here. So let's say for two model A and B, for the first one is the average accuracy is 0.85, but the average confidence is 0.98. And then for another model, the accuracy level and confidence level is almost similar. So which one is better, let's say, calibrated? And we all know the answer, it should be. So for model A, as the confidence level is much higher than the accuracy level, we say in this scenario, it's called overconfidence. And another one, well, it can be under confidence. And we want to make it perfect calibrated. So why we focus on the confidence level? Because let's say, for example, for human, when we are not sure about some base concept or some unknown knowledge, we will say, well, I don't know, or I'm not sure. But for the model, that it will very confidently give the wrong answer. That's why we are concerned about this issue. And to quantify the gap between the accuracy and the confidence level, we use the evaluation metrics, so-called the expected calibration error, it's called ECE. So if we recall this reliability diagram, we can see that the gap between the confidence and the accuracy, which is the yellow part, and then the ECE is to quantify these parts. And this one is for the overconfident. And this one is, of course, is for the underconfidence level. And this is a perfect one. So this diagram I will use a lot times in my later presentation, and which will be look like into this way. So now this for the confidence calibration, there are two well-known technique. One is called label smoothing, which is used in the model training time. This is the part to modify the loss function. And another one is called the temperature scaling. This one is for the post hoc technique, which is to modify the logic of the model prediction. So in the label smoothing, there is one alpha is the smoothing factor, and then here the temperature scaling, the T is the smoothing factor. So my work will use to modify these two factors. Then first one for the label smoothing. So for the label smoothing is like we smooth the true label, means the ground truth. So for example, your true label is always the one hot label in this way, 0001. And after label smoothing, the label can be look like into this way, and only the true label have the highest number. So in this way, we can avoid the model being like overconfident. But here's another problem in here. If you can see this, and well, for this smoothing factor alpha, then we just manually fine tune it. So generally, it's between the value of 0.1 to 0.3 in my experience. So here's one problem in this way, because let's say, well, this one is deliberately make it into blurry, and you don't know what this is. And then for human, we can say, well, perhaps it look like a bird or look like a plane. So even though, let's say, the class 3 is the true label, doesn't mean that the other 3 incorrect label will be like equally distributed. This is not how humans think. So we propose the human confidence label smoothing, which means that we integrate the human confidence into the label to make it like more like the way that we think, instead of this equally distributed way. So in our way, that instead of like in this way, that we make the true label look like this, and which can make the model that learns better and also like more like the human mindset. So here, this is the human confidence, and we also have the model confidence, which is the predict probability. And so this is our proposed method. So this is H1, H2 means the human confidence for one. So let's say for example, the Southampton data set, and this is like 10 different labels. And this is the smoothing factor, and then this is the we will tune this gamma, this value, and we integrate this human confidence inside the label smoothing, this equation, and then we modify the cross entropy loss in this way. And to make the model training is more like human thinking, there's another training way called curriculum learning, which means that, well, we study the math from easy to difficult. And why not let the model also learn the image instead of the randomly learning? Why not learn this into from the like easy to difficult way? So that in the first few epochs, we pass only the easy images, and then later epoch, we gradually add the more harder images inside. And so in this way, the data set we use is called Southampton H. H is for human. So this data set that they have 10 different classes images, and they also like human to annotate each image, so that in this way that we can get some like human confidence in this way. And this is a part that we utilize to modify the label smoothing. And then this is Southampton H is for the image classification. We also have the text classification, which is using the VKR dataset. This dataset is a very interesting one because it asks annotators to look at the image and then see like what kind of feeling you get. And then also you need to write down that why you feel in this way. So this is the source for our text classification. And for the results, so from here that you can see that, well, this is a perfect calibrate line, and the baseline you can see is clearly is overconfident. And then you can see that this is our proposed, like this is the model confidence label smoothing, and the model confidence curriculum learning, this is the human confidence. Then we can see that, well, clearly that the human confidence one is better calibrated. And well, for the VKR dataset, this one looks a little bit messy because one is like because it's asked for the human emotion, so it can vary a lot. And also the dataset is quite small, it's about like 4,000 samples. So from here, we can see that, well, by the number, the accuracy is the higher, the better. ECE is the lower, the better. We can see that this human confidence gave us the better result. And so it's a better proxy for both label smoothing and curriculum learning. So after this label smoothing, and it deals with the overconfidence. Now, how about the other side, the underconfidence part, which is much less explored. And the method we investigate is called the label smoothing. So which means that it's apply a temperature value, which is called P, into the logic. So in this way that you will like click down some like very high value. So if you still remember this one, this reliability diagram is the confidence level, and this one is clearly the overconfident one. After you apply the temperature scaling, it's like the situation can be slightly better. We can see in this way. But there's one problem with the temperature scaling, is like the T value is always bigger than 1. So means it's only deal with the overconfidence class. Then how about the underconfidence class? Let's say in this part, what will happen if you apply the temperature scaling? So means that if you can see in this part, actually it make the underconfidence situation worse. So means that we need a method that can tackle both under and over confidence issue. So this is our proposed method. We call this miscalibration score. And this is the ECE, the equation. So it uses the absolute value of the gap between the confidence and accuracy in each bin. But then how to see the real case, real situation, because you only see this absolute value. So we remove the absolute value, and then the value, the miscalibration score in each bin, it can be like plus, it can be minus, and we can also make it into the class-wise way, just in case that some data set can be imbalanced, and then we apply different weight to all these the miscalibration score to be like plus value means it's overconfident, and then the minus value means that underconfidence, and then we give different weight into this, and we modify this into the temperature scaling. So that in this way that the temperature scaling can supposed to tackle both the under and overconfidence issue. So here's our result. Well, this is a very big table, and because we did the extensive experiment in this way. So this is the green one is for the image classification. This is ImageNet, Tiny ImageNet, Cipher 100 and Cipher 10. And this is for text classification, the SST2, the binary classification. And then this is for the Twitter emotion. And this one is with like 5 different emotions. And then the Twitter sentiment analysis, 3 classes. And because this temperature scaling method is the post-hoc method, so all these transformer-based model is a pre-trained weight actually, and all others is we trained into our way. So you can see that, well, we compare with the baseline, the temperature scaling, and our proposed method, evaluate with the ECE, and then this is the weight subset ECE, which means that you calculate ECE into different classes, and then this is the weight subset, the miscalibration score. So all these are like the smaller the better, because it's showing the arrow. So in this way that we can see, for example, in our method, the ECE is 0.7, and then in temperature scaling is 0.9, and then originally is 2.2. So it means that our method can lower like 3 times down the ECE value in here. And then most, you can see from here, then our method, most of the time, they outperform other Southampton method. So it means that it can really tackle the both sides of the miscalibration. And you can see that for this one, this miscalibration score, because I remove the absolute value, so means it can be plus, it can be minus. So if the value more towards 0, it's the better, but it can be 0. Sometimes it can happen. So means that the value of the underconfidence and overconfidence exactly the same, but it doesn't mean that the model is perfectly calibrated. So it's just a proxy to see the level of miscalibration. And for this one is the ImageNet dataset with the code, this transform-based model and with the efficient net. And then you can see this is the baseline. The baseline is clearly, this is underconfident. So it's very interesting to find that transformer-based model, it actually can be underconfident. And after our method, that we make it like more close to this perfect calibration line. And the efficient net, even though it's CNN, and it still is like underconfident. And when we see the ResNet is clearly like overconfident in this way. So it means that the method, the Southampton method, like temperature scaling, sometimes it can overly calibrate the model, so make the underconfidence level worse. So our method can tackle both of the situation in this way. And we also compare our method with more different methods, like listed in here on the 700 dataset. And well, this one is a very interesting graph. It's called the risk coverage curve. So it means that for all the, let's say for all the test dataset, after we have the inference, the result, and then we rank all the dataset, we rank all the sample of the by their uncertainty score. And we all know that if the uncertainty score is higher, so means that the sample is likely to be the wrong prediction. So here means that proportion referred to experts means that we need to filter out the like 5% or 10% sample with the highest uncertainty score, and we check the accuracy of the remaining data. So means that, well, so this graph actually reflects the reliability of the model. And then let's say that if we gradually remove some percentage of the data, and then you can see the performance, of course, become higher. But one interesting finding is like this graph is actually the is the baseline. So baseline with the ImageNet, and then you can see at the beginning is the swing transformer has the highest performance. And gradually, after you remove more data, is VIT start to have higher performance. So in this way means that VIT is actually more reliable than the swing transformer, even though that is at the beginning is like has the better accuracy. And after apply our technique, well, you can see that still, well, this VIT gradually have the higher performance, but the VIT start to become better when you remove around like 13% point of the data, and then here is after you remove 25% of the data. So it means that our method actually make this transformer more reliable. And with and then you can see in this way then how to quantify it, how to use some kind of evaluation metric to show that in some certain point, the model can be more reliable or trusted. So it comes to our next work, which is about the empirical optimal risk and trust index. So here, I may need to give you a small math question in here. So for example, you have 100 samples and the accuracy rate is 0.7. So means like 30% of the models, the samples are wrong. And in a perfect calibrated sample, if we remove 30% of the data, that means that this 30% of data will be all the wrong data. So the remaining data, the accuracy will be 1. So means the error will be 0. And if you remove 20% of the data and then cover 80% of the data, and you will leave 10 data as the wrong one. So gradually that you will have the error rate is 0.3 in this way. So this is ideal case in the perfectly calibrated model, but we all know that none of the model is perfectly calibrated and then none of the data is perfect. So this is a risk coverage curve, and then you gradually showing that you gradually remove some percentage of the sample, and then you can see the risk means the error in the remaining data. So as I said that there's no data is perfect, so means that we need to remove this kind of inherited error in the model or in the data. So we need to compare the leftover part and then to make it a fair comparison to see the model is reliable or not. So this is called excess AURC. This is area under the risk coverage curve. So it means we need to remove this gray part and only calculate the blue part in this way. So to make it a better visualization, it's generally mean that in here we need to remove this gray part and then we only calculate this yellow part. But there's another question. In practice, there's not necessary or it's not very reliable. It's not very practical to remove all the data and then to see the performance. Then at most, how many data we can remove? The data we can remove the most percentage is until the error rate. So it means that if a model, the accuracy level, accuracy is 86%, and then mostly we can remove like 16% of the data, and then only this pink area means this 16% of the data accuracy or the error is the one that we should focus on instead of the whole thing. So how about, so we say this pink area is as the empirical optimal risk. And you can see that in here, after you remove all this 16% of the data, and then you still have some error. So this error ideally should be 0 in a perfect calibrated model, but it's not. So it means that this can be one index of the model can be trusted, or how much percentage can be trusted. So here's our result, as I showing before in our previous work, that this is for the VIT, and for the swing transformer gradually like is less reliable than the VIT. And to show this, that if you see that this is our proposed method, that pink area, and then you compare this value, you can see that swing transformer, this part is higher than the VIT, and then the trust index also showing the same way. So means that our evaluation metrics can reveal the reliability of the model, and higher accuracy model doesn't mean it's better reliability. So after we talk about all these transformer-based model, then let's come to the large language model. How to quantify the uncertainty of large language model? Let's say we are very familiar with this. And how to check the trustworthiness? We can see the confidence score. It's very difficult because the output is like highly dimensioned. And so that in this way, it's very difficult to extract the entropy. And in the language generation task, such as the question answer or the dialogue summary, so we see the language not only by token or phrase by phrase. We want to see the semantic meaning, and then so we can do the semantic meaning or the semantic entropy to see the trustworthiness. And what if we don't have the access to the model parameter, and we don't have enough resource for the computation? So even though we have all this, then how efficient the confidence or the entropy based uncertainty quantification in this way? So to quantify all, so to answer all these questions, so we propose our method. It's called contrastive semantic similarity. And well, we treat the large language model as a black box, and we use the information consistency to reflect its uncertainty in this way. So for example, for a given question, you have like multiple generations, like 20 or 30. And then utilize the spectral clustering to cluster all these answers based on their semantic meaning or the features. And then you can have the uncertainty score for each generation, and then for one cluster of the generation. So in this way, that we use this uncertainty score to reflect the uncertainty of the large language model. And then our method is actually based on CLIP. So for the CLIP, it's compare the similarity of the relationship between the text and an image. But in our way, that's because we have multiple generation, and we want to compare the pair by pair this text generation. Then how to utilize this? Let's say we have all these generations. Then we modify the CLIP into the vision-free CLIP. So it means that instead of the image encoder, we only utilize the text encoder, and then to extract the feature, and then to compare the similarity between them. And utilize the spectral clustering, which is graph Laplacian in this way, and then get the uncertainty score for each generation, and then use this to calculate the AORC or AOARC. So for the AOARC, this means area under the accuracy risk curve, which is previously the risk coverage curve I show you. And we use the data set of trivial QA, and then co-QA, and then NQ in this way. And then we use 3 different large language model. This one is for GPT is for 3.5, so the API way. And we compare all these different methods, and this is ours because we utilize the spectral clustering. So it has utilize the eigenvalue and eccentricity and the degree matrix. So in this way, that from this accuracy rejection curve, you can see that our model, our method can make this can have a better like the way to quantify the uncertainty. And for the AORC, it's also showing the similar result in this way. So well, here I will not explain the how the spectral clustering is work, but I'm happy to that after this presentation. And so after dealing with the large language model in the black box way, so we look into then in the fine tuning, then what other problem is there? So one important one is called the safety alignment, because for the large language model, it's very easy to break its safety property. Let's say when you ask some like malicious or the toxic questions, for example, like how to poison other people, it may give you the correct answer for this instead of saying that, well, I cannot assist you or give you other different advice. And some literature has shown that the LoRa fine tuning can actually weaken such safety alignment. And so to solve this question, the recent methods, they always need to have a trade-off between the performance and the safety alignment. So performance means you either is the accuracy or the Roche score or Mathieu score or something like this. And also, well, after you identify that like what kind of parameter caused the problem, and well, people can use this pruning way to make the model is like smaller and more safer. So in this way that we use our proposed method is called the layer-wise projection-based method. So means that we compare layer by layer of our LoRa training model and the pre-trained model. So here, for example, we use the Llama 2 7B chat as the pre-trained model, and then we set the parameter as aligned, because we assume that the pre-trained model has the best alignment for the safety. And then of course for the LoRa fine-tuning model, we set this as the unaligned. We compare the layer by layer way. So in each layer, we subtract them and then create a subspace by this projection method. So means that if later when we compare this the projected LoRa weight and the LoRa weight, so means that if the similarity is high, so means this LoRa weight is falling inside this safety alignment subspace. Otherwise, like it changed too much, so we need to either replace it or we need to filter it out. So this is the this is a base idea. Then we say that I need to compare the similarity between this. This is actually two very high dimension metrics. Then how to compare them? The recent work, the safe LoRa, used a very naive cosine similarity between them. But the fact is, the large language model weight is very high dimensional. For example, like 4.96 times this. So for such high dimensional metrics and with then with a high sparsity, the traditional similarity method, such as the cosine similarity, Euclidean distance, is actually not suitable for this comparison. So there's a recent work called dimension insensitive Euclidean distance, which can compare for this kind of like high dimensional metrics, but it's not designed for the large language model. It's statistically theoretical work. So how it works in this way, for example, that you have two metrics, A and B is all very high dimensional, and then N is the dimension. So it has the expected distance, calculate in this way, and then calculate the Euclidean distance. So it also has the max and mean possible Euclidean distance in this way, and then the variance. And then it's calculated in such way that, well, this part is for the scaling. And so as I say that this is the theoretical work, then we need to redesign this to the that it can be suitable for the large language model. Then what problem it has? The first one is in this variance, because it can be easily biased to the extreme value in the matrix. And then large language model, each layer, the weight can be, sometimes it can be like very extreme value. And another one is the expected distance, because in this work, it assumed that all the data distributed in the Gaussian way. But in our model, the weight is actually not in this way. So this is the modification we do. And then this is also the way that we redesign this DIEM, and then we call this empirical DIEM. First one, we replace the expected distance. And we replace the standard deviation with the IQR in this way, so to remove the effect for the extreme value. So this is so after modification, this is our proposed method to measure the similarity or the difference between the layer-wise weight. And then we also use this as a guidance for the LoRa pruning. So we set a threshold. If this if it's like smaller than the threshold, we keep it because this is a distance value. And if it's larger than this, and then we prune it. So this is the overview of our work. And this is the pre-trained model aligned 1, and then this is the unaligned the weight. And we compare the distance between these two weights, and we decide to keep it or to filter it out. Then here's our result. So we have used the model of Llama 2 and Llama 3, and we used two different sets of the evaluation metrics. One is called the utility, which is the higher the better. and another one called safety metrics. The lower the better, the attack successful rate and harmful score. So in this way that you can see that this is our method, and then this is for the pruning, and then this R means replacement, means that we didn't pruning this. Instead, we keep it, we replace with this projection value, because the previous literature has done before, and then in this way that we can see that well, our method still outperform the SOTA method, such as this the CIFLORA and this BEA. So this one is based on the dialog summary, 1,000 samples plus the pure byte dataset, 100 samples. And another set of the experiment is on the alpaca dataset, 1,000 samples, and the pure byte dataset, 100 samples also. And we didn't show that the result for the Llama 3 because the attack successful rate is too high for other methods. So means that it's not plausible for us to calculate like other methods in other evaluation in here. So instead of this, we purely use the alpaca dataset for the fine tuning, and then still that our method like behave better in this way. So that you can see that our method, there's no trade-off between the utility and safety, and also can improve the performance. So here is the risk coverage curve. This is for the dialog summary with the pure byte, and then you can see that our method still like after you remove certain percentage of the data, the performance is still better. And then for here, is on the alpaca dataset. So you can see that for the LoRa fine tuning, even you remove certain part of the data, it's not even go the performance didn't even go better in this way. And another very interesting finding is, well, we compare the let's say that we need to filter out some layer of the large language model, then which layer we are filtering out? We are filtering, and because there are 32 transformer blocks, and then inside we test on the like K and the key, yeah, the key and V in this way. So like let's say for this CIFLORA, the previous method, that is only focused on the very first and then very last blocks. And then we all know that for the very first few blocks is for initialization, very last is very sensitive for the answer generation. But but in between these blocks is important to catch and learn the features. So it means that our method can better catch the like when the weight didn't learn when the weight didn't learn good enough features in this way. So instead of just focus on the first few and then last few layers. And because we're pruning some layers, so it means that our inference time also become shorter. And then you hear that we almost half the inference time in this way. So well, for our recent work, and then in our lab, so one work we are doing is we try to build this large language model based multi-agent system. And so well, because our work is mainly to make the AI system more responsible, so for each step of this agent, such as like this rack system in the memory or in the planning or in the final decision making, we will implement all these uncertainty quantification methods to make it more responsible and trusted. And another one we are doing is for the as we look into the medical domain. So for to deal with the multimodality data in the with the large language model. So for example, for the data set, this is one the CT scan, and then have the question and answer in this way. So so we are trying to deal with the let's say the medical report generation and how to evaluate to integrate more human principle in this way. So for the summary of the talk, and for my work. So we have looked into the confidence calibration to tackle both sides, and also the automatic failure detection to make the model more reliable and trusted, and then the uncertainty quantification for the large language model, both in the black box way and in the fine-tuning way, so to make the model have the better safety alignment. And here is our code and the pre-trained weight. Thank you for your listening. So any questions?
Yes, thank you very much, Shoang. I noticed, and I think it's really I really appreciate that you tried to put a lot of material into this 40 minutes. So we have really a lot of things to note from your talk. I see already there is one question in the chat. I wait until we have a bit more, but let me just start with one myself. I'm coming back to your very first experiment on confidence, because at the end you are showing something like 20 different evaluations of different models, and you said at one point in time that it was really a lot of work, and we know that there's a big challenge for the evaluation of AI systems, of large AI systems. So your first, these ones, in fact, you are working with, I would say, rather small models or not so big models as the ones that people are manipulating now. So would it scale up to the large model that people are using now?
Well, let's say you mean for this
Yes.
part, then yeah. So it's a lot of experiment.
Yes, it's a lot of experiment, but I see, I see some ResNet, I see some BERT, which are much smaller than the models that people are using now.
Yes, that's true. Yeah, it's correct. So so because this work is like 2 years ago, and yeah, so by that time this kind of large language model is not hasn't come out yet that much, I think. So this is this models at that time is like the SOTA model. Yeah. So of course compared to now, it looks like too small, but at that time, I mean back to 2 or 3 years ago, it was like the most advanced one.
But would you be able to do the same with the current models?
Well, for the current models, I think it's fine to do the same. But for the large language model, there's one question, because all these are the image classification task, and then for the large language model, it's mainly for the language generation. So if we force the large language model to make it into to classify the image, it kind of damage its capacity. So from my point of view, that's not all the models are suitable to do to conduct this kind of experiments now.
Okay, I see at least in the chat a few questions by Brian Jalayan. So the best maybe, Brian, is to ask them directly. Hello, Brian.
Yeah, hi. Yeah, a great talk. Lots of interesting work. I'm very impressed. Thanks for the talk. So how sensitive is this pruning threshold that you have for different tasks or different data sets? Did you try on to see this works really just on one data set, or how does that work? Can this be kind of dynamically adjusted?
Yeah, so for this threshold actually is it's dynamically adjusted. It's like in we select, okay, so we calculate all the distance for all the layers, and then we select the top 10 or the least 10 layers as the threshold. So it's not, so it's not like we set it into this way, and then I choose top 10 or top 15. It's because to follow the previous work and to have a fair comparison. But I didn't try top 5 or top 20, 30. This kind of threshold.
Yeah, very interesting. And did you try this spillover on some sort of harmful data or adversarial attacks?
Yes. So the harmful data is this one, the pure byte. This is the harmful data. And then in the fine-tuning time, we mix the dialog summary data set with the harmful data set, and then also with alpaca. So this is the harmful part we have.
I see. Yeah. Thank you. Thanks for that. What about the scalability? Like LoRa is very efficient. Does EDM, like, is it going to be as efficient as LoRa from computational perspective?
Yes, it's quite yeah. So we have tested this this inference time. Well, I have to say that compared to the cosine similarity, it has like more computational time. I have to say this, but it's not like that much high compared to other methods also. Yeah.
Thank you so much.
Thank you.
Steve, yeah.
Thank you, Shoang. This was a really great talk and very, very interesting. And I like how your work builds to the conclusion, showing some of that scaling. My question is a little bit related to Bertrand's, not so much from a scaling perspective, but it looks like the confidence score was originally, developed on a classification problem or a set of classification problems. So my question is, how different perhaps is that score? Obviously, coming up with a single measure is always nice, but if you have true positive, false positive, true negative, false negative, and the variations like precision recall, F1, MCC, how different beyond providing one score is that confidence measure from those? Why not just go with those or use something like MCC, which sort of puts it all together in a summary statistic?
Well, I think for the confidence score, because it's the predicted probability, and then people use this to calculate the further like accuracy or F1, such kind of score. Well, we always say that the confidence score yeah. So for the accuracy, let's say for example, of the F1 or precision, this kind of score is like I want to say that it's more like a theoretical like evaluation work. So for people to see, but if you want to apply to different domain, people have different principle, different regulation, different focus. So this kind of score perhaps may not be that much relevant or useful.
I see. I was thinking, and this is just a thought maybe for your further consideration, but if you want to talk a little bit about it, I'd be interested in your perspective. But if your classification problem is heavily skewed, dealing with accuracy and confidence is going to give you a skewed perspective. Thus, in cases where there are, basically data set bias or underlying bias, it's going to be shifted in that direction, or at least I would think so. I'm not sure myself. It's just I've been working in some of these problems, and that's been my observation in classification problems like that, which again go to that scale. But it's up to you as to whether you want to address it. I don't want to commandeer too much of your time. There are other questions.
Yeah, it's fine. So for the confidence score, yeah, of course, that's when some class have the data imbalance issue, and then it can be biased to the like majority data. And so I've seen some work that people doing this kind of like inter data or inter class classification. So instead of like classify that all the whole data set, we focus on inside one class, and then to see that inside this one class that how many like bias or different like confidence score that we can see. Yeah. So I think this is perhaps like the way you see it. And then I think this problem is related to like fairness. Yeah. Yeah, if I'm not wrong.
Thank you.
So I noticed that the next question is also from Florida. So I think that you raised some interesting points for people in Florida. That's interesting. Johnny, your turn.
Oh, yes. Well, thanks for this great talk. I was interested in your last few slides that you actually applied this into a multi-agent system. And I was wondering how it can help making this safe decision, or like how you can qualify this so-called safe decision within the agent, and maybe express a little bit of maybe like how it can it be applied. Like I guess it's on the agent side, but is there any other thing that related to, for example, like memory side or any data, like input data, and how it works?
Yeah, because our work is well, this agent part is still the ongoing work, and well for us, like the our let's say the step is first to make each step of the agent part to be responsible, and also and then later to make the whole decision part responsible. So this is our way. And then, for example, let's say for this memory for the rack system, and then we can quantify the quality or the consistency of the information retrieval, and then for the planning or the reasoning, we can we currently working on that, how to make it reasoning or the rationality. So we need to quantify that how, like, yeah, so how much good it or bad is the reasoning is. So yeah, so let's say for the last final decision making, we apply the conformal prediction, this part. So for us, it's all related to the like uncertainty quantification, and then the whole the final purpose is to make the whole system like responsible.
Got it. All right. I appreciate it.
Well, thank you.
So I don't see other questions in the chat or no hands raised, but I have some kind of a big question for you, Shoang. But it's in fact, yeah, but it's also a question for everyone. I was recently reading the AAAI report on the AI research challenges. It's a recent work that has been published, I would say maybe 1 or 2 weeks ago. They have a section on AI factuality and trustworthiness. And they say, they're right, improving factuality and trustworthiness of AI systems is the single largest topic of AI research today. And while significant progress has been made, most scientists are pessimistic that the problems will be solved in the near future. So we all work on the matter, and you have shown some progress. So what do you think of this sentence by AAAI scientists?
Well, well, for me, because I'm still like new in this domain. So from my experience, that's, well, when people raise a big question, I don't see that it can be solved by a single method or can be solved within a short time. It's all the incremental research or incremental novelty for this. So I feel that, well, in the near future, then depends on how you define the near future.
Okay, yeah, maybe 10 years.
Yeah, it's very difficult to say, but
no,
one thing that
it's a difficult question, I know. In fact, we are all working in this direction in order to improve trustworthiness of systems, but we know that it's a long story, huh? And but we are all contributing. Yeah, someone asked me to provide the AAAI reference. I will do that in the chat. But yeah, I think at one point in time, they also write that in addition to the technical work on and scientific work on trustworthiness, improving this performance index and uncertainty and confidence, etc., we should also do it with looking at risks analysis, which is it's not your subject, I know, huh? But it was the subject of our first ATRASS 2 months ago. So that's maybe some kind of interim conclusion to the discussion that we had. At least let's thank you a lot, Shoang, for this very a complete talk. I think it has been appreciated. Yeah, you can use your, I don't know how it is. You can clap your virtual hands as you like. Yeah, they are doing it.
Thank you, everyone.